This is CPE 233. This is Introduction to the course as well as Introduction to Memory. So the course overview, the course is Assembly Language Programming and Computer Design, not necessarily in that order. So the idea is we are going to study a computer architecture. So computer architecture is just a bunch of computer modules that form the computer and how they're interconnected. So we'll be studying that. And additionally, we will be working on assembly language programming, which is essentially a low-level programming of the computer. And so we'll be working really close to the hardware relative to probably the way you're used to programming computers. So in to be specific, in this class, what we're going to do is build this computer based on a given computer architecture. So we're going to actually give you the architecture. You're going to build it. Once you build it, you're going to program it with the assembly language, write a couple programs. And then the notion here is the experiments are essentially, there's 9 experiments. 1 through 7 represent a step-by-step build of the computer itself. And the last 2 experiments are, you're not doing any building with Verilog, you're just actually programming it with assembly language programming. So this is the fast overview. What is a computer? Essentially, a computer is a device that sequentially executes a stored program. And so the important thing here is there's a program and something's being executed. So this right here is the accepted super basic computer model, and it shows the 3 basic parts of the computer, which are a processor, which grinds the data. There's a memory, which essentially stores data and particularly stores your program. And then, of course, you have a way to talk to the computer. So this is your I/O. Data comes in to your computer. Computer sends data out to the outside world. The memory is used to transfer data and program, and with this processor you can crunch data. So that was an extremely low-level version of computer. We want to bump it up here a little bit, and what we're going to do is expand out on the processor module, and then we're going to expand out on the memory module. So the memory module in a typical computer has 2 types of data in it. One is the instruction data, which is the program itself, and typically you have other data, such as just other places to store stuff that's not programmed. The I/O, nothing too exciting about this one, but we've broken the processor up into 2 units. One is the control unit, and one is the CPU, which is central processing unit. The notion here is the control unit, just like you learned in 133, is a circuit that controls another digital circuit. It so happens that in this circuit, it's controlling the CPU. Part of the CPU is the ALU, which is essentially yet another number crunching module. And the important thing here is I can trade data back and forth between the CPU and the data memory. And once again, this control unit, it's accepting status inputs and it's sending out control outputs. Those control outputs are to the modules in the computer. They're used to control the flow of data through your circuit to get whatever your program wanted you to get. There's accepted 3 levels of programming in the world here. Essentially, computers are giant digital circuits, so the only thing they understand is 1s and 0s. 1s and 0s represent the machine code. Now, those 1s and 0s are once again going to control the flow of data through your computer. So we're not going to do that. That's too low level. I know computer science people like doing that, writing programs in machine language, but it really serves no purpose. You're probably used to operating at a high level like this, where you wrote a program. Here's your code here, and then you maybe compiled it, and the compiler generated the assembly code, and probably the compiler at one point generated the machine code as well. So we are not at this point. We're going to take this middle approach, which is you're going to write assembly code. You're going to send it off to a piece of software called the assembler. The assembler is going to translate that assembly code into machine code, and that machine code is what's going to be downloaded onto your computer. So 3 levels of programming, machine code, very low level, high level programming, and this is assembly language programming, which is, we'll say, hardware specific. This is the part of the cheat sheet here, and these are probably 2 important photos here. Essentially, it's the programming model or programmer's model, and it's also the instruction set. Now, this is the programming model, programmer's model. These are the hardware resources available to the programmer. And so essentially you got a bunch of registers, another register, yet more registers, and then a big piece of memory. And now if you notice here, this memory stores both program and we'll say data. So how do you control all these registers? Essentially through the instruction set. Here's the instruction set. This is, I don't know, 40, 50 instructions. I forgot how many. But the important thing is relationship between these two. This is the hardware the programmer can control. The programmer controls that hardware by issuing these instructions. So this is the RISC-V adder. This is a slightly older diagram, but it works. So once again, this is the instruction set and programmer's model. This instruction set kind of implies a certain hardware, and here's the hardware. Now the idea here is this hardware is set up or configured in such a way that it can successfully implement those instructions, which means, of course, it has these hardware features involved in it. So once again, here's your register file here. Here's your register file there for an example. But in summary, this is your instruction set. It needs to be implemented on some hardware. This is the hardware we're going to implement it on. This is given to you. This is the RISC-V adder. So memory is our first real topic here that we're going to delve into. And many types of memory out there. There's just so many types out there. It's just not even useful to talk about. But I like breaking it down into 2 types of memory. Essentially, I call it incidental memory and structured memory. Okay, incidental memory is like a flip-flop or a register here or there, where a structured memory is something large, such as like a RAM and ROM, which we'll talk about next. Now, these structured memories is where we're going to spend a lot of time. You've already worked with flip-flops and registers in 133, so that should be familiar to you. The structured memory, it's analogous to arrays in a higher level programming language. In hardware, essentially in software, an array has a set of values that you can write to it and you can read from it. So based on an index. So to get at a particular piece of data in an array, you use the index. Now in hardware, it's very much the same thing. What you kind of have is a whole array of registers or a whole set of registers. The registers you're particularly getting at is decided by the address. So each register, roughly speaking, has its own address. Generally speaking, when you talk about structured memory, people really don't talk about registers, but it's a way to abstract it in your mind. It's very, registers are something we used, arrays are something we've used in your programming classes. So this is your basic memory right here, and it has 3 types of inputs. It has some control inputs, it has some address inputs, and it has data inputs. Now the data here is written in a bidirectional way, so data is going to be coming into this memory, and data is going to be going out of this memory. And which data in particular goes in and out is decided by this address. And lastly, to get what I need done on this thing, I need some control signals, and that's it. Data, address, and control, which is 3 types of inputs to our generic memory module. So these memories can do 2 operations. They can read and write. So reading means I'm taking something from this memory and copying it somewhere else. So this is your read operation. I'm going to essentially give it an address give it the correct control signals, and I'm going to get that data out. Now, read operations typically don't change memory. It just reads from, it just copies what's in that memory and makes it available to the outside world. The write operation is going to change memory, and what's going to happen here is data is going to go into this thing from the outside world and get written in that memory. And once again, these write operations actually do change the memory inside this box here. So these are two basic operations. Read is retrieve data from the drive. Write is write memory to the write data to the memory. So read and writing memory, typically the vernacular we use all the time. Anytime we talk about memories, we are typically interested in the capacity of the memory, how many bits it can hold, generally speaking. Now this is our generic memory object here. Once again, it has the data, control, and address, blah, blah, blah. But we actually, what we're interested in is just this terminology here. And what you see here is a couple of things. Now this S essentially is the word size, and it's the width of the data that you input and output to this thing. Now, typically speaking, you get this, essentially the smallest chunk of data you can get out of this thing is the word size. Now, it's not necessarily 1 bit. Quite frankly, most memories are not bit addressable. You have to get a chunk of memory out of there, like a byte or something bigger than a byte. But this is the data width. This is the word length. The word length associated with memory has to do with the width of the data that comes in and out of the memory. So this value right here is the width of the address lines. Now this is going to be a classic binary thing here, where the chunks of S that this memory can hold is determined by the width of this data signal. So essentially, it's going to take those data lines. If, for example, if there's 8 data lines, that means I can have 256 different unique bit values for an 8-bit number, and so that would be a memory that can hold 256 chunks, that all the chunks are S wide. Anytime you're talking about memory, you talk about memory in bit capacity or byte capacity or word capacity. It's always contextual on how you want to do that. The important thing here is this 2 to the n relationship with 2 to the m with the address lines. So typically I ask this question is, how many address lines does this particular memory have? And people say it has 4,000 address lines. And so anytime you work with these problems, put some horse sense into them. You're not going to have 4,000 address lines. So a couple examples here is we're going to list these memory sizes in bits and bytes. So this is going to be bits. It's 4 times 16 bits, and it's 4 times 16 divided by 8 bytes. So this is 512 by 32 bits, or it's 512 by 32 divided by 8 bytes. And this is important. This is 2 times 1024. It's the k is actually 2 to the 10th. 2 times 1, this is 2k, so I'm going to write that down. I'm not going to put 2,000 here. It's actually 2 times 124 times 24 bits, which equals 2 times 1024 times 24 divided by 8 bytes. Okay. So there are tons of types of memory out there, but they generally fall into 2 categories, and that's ROM and RAM. So ROM, read-only memory; RAM, random access memory. So these definitions don't have really super literal meanings. For example, random. What does random mean? Well, random refers to the notion that you're able to get at be it both read and write. You're able to access that memory no matter where in memory at the same amount of time. So the access times are going to be the same. Now this is special because devices like tape drives and hard drives, the spinning hard drive, are not random access. It will take a variable amount of time depending on where you are on the read heads or where you are in the tape. So the functional differences between RAM and ROM are: RAM, typically you read and write it. ROM, you can only read it. The other important thing here, RAMs are volatile, which means you lose the data when you turn off the power. ROMs are non-volatile. You turn off the power, turn the power back on, and your data is still there. So once again, the final word: RAMs, readable, writable, volatile. ROMs, typically read-only and non-volatile. Now, there's always has to be some way to get data into a ROM, and typically you can write it there, quote, write, but the notion that it's non-volatile makes it into a ROM. So this is our foundation module for a RAM. There are some, just looking at this thing, you don't know whether this is the reads and writes are synchronous or asynchronous. Someone has to tell you that, or you're going to have to look at the models. So this is the input data and output data. Both of them have the same width. This is the number of 2 to this m numbers, and number of chunks of data that are n bits wide that this RAM can hold, etc., etc. So this may be synchronous or asynchronous. Someone has to tell you. This is the code for the RAM, and it's nothing super interesting here, but here we have the pause edge, and anytime I use a pause edge, that becomes a register of everything assigned in there, so that makes this memory register. As you can see in this thing, the pause edge is based on the clock, which makes essentially this write operation is synchronous. Here's the read operation. It's not based on the clock, so therefore the read operations are asynchronous. This is just one generic model that we use quite often in this class. That's why I'm showing this one. There could be many other things. So lastly, there's our architecture. It's the end of every lecture slide. And okay.